So we're looking at the differences between instruction set architectures, and there are a number of features we've already looked at. Branching is one where there are really two very different approaches, and so it's worth looking at the different approaches. Basically, the question is, am I checking a condition right now, or am I branching on a condition I checked before? If you have an instruction set architecture that uses flags, then you are separating out the condition check from the branch, right? And ARM does this, sets these flags. x86 does this, it sets the flags. LC3 does this as well. And then when you branch on those flags. And this is very useful and powerful because you can set those flags from any ALU instruction. You can compare based on a subtraction, you can compare based on exclusive, or anything you do in the ALU, you can then make a branch as a result. So it's incredibly powerful. But like I said in the previous video, you have this problem with pipelining, that you have a condition that is set in one instruction that is then checked in another. And so those internal hidden states can make debugging very complicated, can make pipelining very complicated. So modern reduced instruction set machines like RISC-V and MIPS use comparisons within the branch itself. So the branch instruction contains the comparison that you're doing, contains the registers you're comparing, and then the target address. So the example here, branch if equal R1, R2. And so you're going to look at R1, R2, you're going to compare them for equality, and then you're going to branch if they are equal. Now, there's a problem here because your ALU is not in that state in the pipeline, right? You can either have the ALU do this comparison, which is going to be in a different pipeline stage, or you're going to need fundamentally separate comparison logic that is going to be checking whether these two things are equal or unequal. And as a result of that, most architectures that implement explicit comparisons within the branch have very simple explicit comparisons. Branch if equal, branch if not equal. Sometimes they might do like a branch if less than. But usually it's just branch if equal, branch if not equal, because then you can have another instruction that's going to set some other general purpose register to a complicated state. Right? If you want to compare with XOR, or you want to compare with subtract or something like that, you can do this in one instruction, set a general purpose register, and then branch if that general purpose register is equal to or not equal to 0. If your comparison failed, you'll get a 0 in that general register, and that way you can branch on that 0. And this is why most instruction set architectures that have an explicit comparison within the branch also have a 0 register to compare to. That allows you to always have a sort of a source of truth. The number 0 is part of your register files. You can always compare to that. And then in MIPS, for example, you would use an instruction like set less than to set a register to a value of 1 if A0 is less than A1, and then it would be a 0 otherwise. And then you can compare that register to your 0 register and branch on that condition. And that reduces hazard penalties, that makes pipelining easier. It means there are no hidden states to screw up your debugging. So that's why this is a decision that sometimes instruction set architectures will make. The other thing that is worth talking about is how do they represent immediate values? This is another thing that is sort of, it seems simple. Well, the immediate value is just data in the instruction. But different instruction set architectures implement this very differently. So x86, of course, because it's variable instruction length, it just puts the immediate in however many words after the instruction are needed, and everything's fine. If you want a full word of immediate, it's right there, right? If you're not going to do that, if you're going to have your immediate value be part of your instruction, then it has to be smaller than 32 bits. And so you have to have some way to expand that to a 32-bit number. The two ways to do that are clever representation, so different ways of putting the information in such that it can be expanded, or multiple instructions that allow you to compose a 32-bit number. And so we'll look at both of those. Right? In general, the target of this kind of design decision is make the common case fast, make common values implementable by one instruction, or the other way to do this is to load common values from a pool of literal values that are stored in memory. That can slow things down because you're doing a memory access instead of an immediate value. But in general, we want to have the most common immediate values be accessible within the instruction. So a few different ways to do this. In MIPS, what they do is they take half of the instruction and make it the immediate value. So you have 6 bits for your opcode, and then 2 5-bit registers, and then the remaining 16 bits are the immediate value, and you just take that and do a sign extension to make it 32 bits. And in general, this is really, really powerful because you can have a number up to, what is it, 64,000, which is, you know, most of your simple literals will fit in there. And then if you have one that can't fit, you have a combination instruction where you do a load upper immediate, and that will take that 32-bit immediate value and put it on the top half of a register, and then you just AND together or add together with another immediate value, and so you can compose a 64-bit number by putting two 32-bit numbers together. So you get access to the full range of immediate values. Small, simple, common immediate values can be accessed in a single instruction, and at worst, you have to use 2 instructions to compose a 32-bit immediate value. So that's the MIPS way of doing that. The problem with this is that you have thrown away a register, right? Usually in MIPS you have 3 registers, but now with this method you actually have to throw one of the registers away to get a full 16 bits of immediate. And so as a result, you have to have one of your registers be either a source or a destination. And so they have register S for a source, register D for a destination, and register T. And register T can be either a source or a destination depending on the kind of instruction you're executing, and that can be confusing, and that means additional hardware to design that. So that's the design compromise there. You lose a register, but you get full access to whatever immediate value you want at most 2 instructions. LC3 does things a little bit differently. It has a lot of different immediate fields depending on the instruction that you're executing. ALU immediate fields are 5 bits long, tiny, right? 0 to 32. Load stores are 9 bits long. Branches are 6 bits long. Loads and stores and branches are 9 bits long. Load register are 6 bits long. So there's lots of different sizes of immediate values depending on what you're doing. That's means that you get the most sort of access, the best. What am I trying to say?